So in the previous lecture, we've calculated density of states in the presence of a magnetic field. And we noticed the following. If this is my energy axis, this is my density of states. In the absence of a magnetic field, I have a dependence, of course, which is proportional to the square root of the energy. This is the conventional density of states in a 3D solid. Now if I switch on a magnetic field, in the presence of a magnetic field I get these singularities. And we analytically derive the existence of these singularities, right? And these singularities result from the quantization that is imposed by the magnetic field, that is the Landau quantization. And these singularities are called the Van-Hove singularities. Now what we would like to find out is what is the role of these singularities and how do these singularities affect various phenomena such as the resistivity, the Seebeck effect, the magnetization, etc. in the presence of a magnetic field. Everything is encoded within the density of states. And if we have a Fermi level inside a metal, for example, if the Fermi level is here, if this is EF naught, the Fermi level in the absence of a magnetic field, there is a certain density of states at this energy. Now imposing a magnetic field has two effects. The first effect is that the spacing between these singularities, which is given by h bar omega c and is proportional to the magnetic field, is going to change. So these singularities are going to dilate, they're going to stretch. The second possibility is that it is also possible that this Fermi level might change in the presence of a magnetic field. So there are two effects. And you have the constraint that the total number of electrons inside the solid must not change. There is only one constraint. So what is the effect of the magnetic field? There are two possible effects. First effect is that these singularities will change, the spacing between them is going to change. Because the spacing is proportional to the magnetic field, it's proportional to omega c. So these singularities might dilate or contract. The second possibility is that the Fermi level itself might change in the presence of a field. There are two effects, and there is one constraint. The constraint is that the number of electrons per unit volume is not going to change, because the size of the solid remains constant and the total number of free electrons that are available remains constant. Okay. Now, so what we would like to do is, first of all, we would like to see how does the Fermi level change. We know how the magnetic field changes the spacing between the Landau levels. It's just proportional to omega c. No, the Fermi level. Let's see if the Fermi level changes. The Fermi level does change because you have this constraint of keeping. You see, so when you impose a magnetic field, it's possible that these singularities shift their position. So now you have fewer Landau levels within the Fermi level. Okay, but you want to keep the total number of electrons constant. Now the degeneracy of each level is fixed. That's given by the magnetic field and the area. So what's going to happen as soon as the Landau level crosses the Fermi level? The electrons in higher levels must repopulate themselves within the lower levels, so that the total number of electrons inside the solid remains constant. It might be possible that such a reconfiguration is not at all possible without a shift in the Fermi level. So we have to see whether the Fermi level changes in the presence of a magnetic field or not. For that, I introduced the concept. So it's going to be a lengthy, involved lecture today with lots of mathematical ramifications, and we're going to do lots of calculations, numerical calculations. So it's going to be an involved lecture today. So first of all, I would like to introduce the concept of the integrated density of states. Now the integrated density of states at some energy E is defined as dE prime G prime from 0 to E. Okay? So it's just a state counting operation. Just count the number of states. G. No, this is going to shift its position slightly. This level is going to shift. And the density of states, of course, also changes with the field. That's clear. It's just dependence upon B. Now this is the integrated density of states. For in the absence of a magnetic field, we've already calculated the density of states as a function of x. And that is given by, this was our previous lecture, this is given by the density of states at the Fermi level. 0 shows the absence of a magnetic field, under root x naught x, where my x is defined as E over h bar omega c. It's a normalized energy. My x naught is defined as the ratio of the Fermi level in the absence of a magnetic field with omega c. Okay? So this is the density of states in the absence of a magnetic field, and in the presence of a magnetic field. If you recall from the previous lecture, we had half G E F naught over under root x naught sum over x 1 over x minus L minus half under root, where L goes from 0 to LF. So this is in the presence of a magnetic field. And if I plot this function, I get the yellow curve. And if I plot this function, I get the white curve. I can plot either with respect to the energy or with respect to x. Doesn't matter, because these are just rescale variables. Now what I would like to do, I would like to find the integrated density of states in the presence and absence of magnetic fields. Okay? Remember that this operation physically is just counting, it's a state counting operation. This is the density of number of states per unit volume per unit energy. You integrate over energy, you get the total number of states per unit volume. So this is just a state counting operation. And electrons can fall into these states. So you need to know how many states exist. And you know how many electrons there are. So you compare this n with the integrated density of states. So this is the container in which electrons are going to fall in. And you know the total number of electrons. So that's why these integrated density of states are important. So let's calculate the integrated density of states in the presence and absence of fields. So first of all, G naught x. In the absence of a field, I have to integrate this. Everything is a constant. Alright. So when I integrate with respect to energy, I know that energy equals x into h bar omega c. Yes.
Sir, but I have still not understood what the function capital G of E represents.
Leave suppose that I battery बदल दे. Do you understand what small g represents? So small g, number of states per unit volume per unit energy. You multiply this with energy and integrate over all energies, you get the total number of states per unit volume. Up to energy E. So up to energy E, how many states exist? Which are placeholders for electrons. And electrons can go into these states. जरा बदल देंगे ना, लाइट क्यों जल रही बार बार?
Alright, so let's calculate this integral over here. So I have to integrate this. So G E F naught over x naught under root dx prime x prime. Okay. So I'm integrating, I'm taking x to be my variable. Now what I need to understand is that since I have this factor over here, dE prime is x times h bar omega c. So I put in an extra h bar omega c here. Okay. Because I'm integrating with respect to energy. And I'm changing my variable. So this is x goes from 0 to some x. Now this object here is G E F naught h bar omega c x naught 1/2, and this is 2/3 x naught 3/2. G naught x equals 2/3 G E F naught x naught raised to power x naught divided x naught into h bar omega c, which is E F naught.
Alright, so this is the integrated density of states in the absence of a magnetic field. Check whether this is correct or not. Okay, let's check that. Let's put x equals x naught, that is we're going up to the Fermi level, then the integrated density of states must be equal to the number density of electrons. How many electrons exist per unit volume, okay? So if I'm going to check this, when I check this, G naught at x naught corresponds to the Fermi level, EF naught. This equals 2/3 GEF naught oh, this is x. This is x. This is x 3/2 over x naught half. Into h bar omega c. Let me rewrite this again. So my integral G naught at some x equals 2/3 G at EF naught h bar omega c x 3/2 divided by x naught 1/2. Now I'm going to check this. At x naught, this is 2 over 3 g ef naught h bar omega c x naught 3 by 2 minus 1 by 2 is x naught. Now this thing over here is ef naught. Now this object over here, we know from basic solid state physics, equals 3 over 2 m over ef naught. This is n, as it should be. So if I integrate up to the Fermi level, then the total number of states, the total number of available placeholders is equal to the number of electrons. This is how we define the Fermi level. So this is a correct calculation, and it shows that g naught x is proportional to the 1.5th power of x. Everything else is a constant. Okay. So we've calculated the integrated density of states. Now let's calculate the integrated density of states in the presence of a magnetic field. So which means that I have to integrate this thing here. So I obtain 1/2 g ef naught divided by x naught under root. Now I have to integrate that object. Okay? So if I integrate that object minus half, I get 2 times integral of x minus L minus half under root, where L goes from 0 to LF. Okay, so 1 over under root. So when I do the integral, I get, so power is minus half, so I get minus half plus half. This is what the integral is. This half goes away. I'm left with this. So in the presence of a magnetic field, the integrated density of states is g ef naught over x naught, and of course there's an h bar omega c as well, because I'm integrating with respect to x. I'm changing the variables. So g ef naught h bar omega c sum over the Landau levels x minus L minus half, where LF is the maximum L such that L plus half is less than x naught. Okay, this comes from our previous lecture. So this is the integrated density of states in the presence of a magnetic field. Now what I could do, now I would like to compare this thing with this thing over here. There's a factor of g, there's x naught over 1 over 2 here, and there's x naught here. So what I could do is the following. G naught x equals 2 over 3 G E F naught. So what I would like to do is an h bar omega c is x 3 by 2. I insert an additional x naught here. If I insert an additional x naught, I have to insert an additional x naught here. Okay? Now h bar omega c x naught is E F naught. So this is 2 over 3 G E F naught. This is E F naught x 3 by 2 over x naught 3 by 2. So I've just manipulated G naught x a little bit. Now I would like to manipulate this thing a little bit. So if I look at GVX, GVX is G E F naught h bar omega c. Now x naught is E F naught over h bar omega c square x minus L minus half. So what I could do instead is I want an x naught 3 by 2 in the denominator. Okay, so what I could do, I already have an x naught. I insert another x naught under root in the denominator. For that I need to insert an x naught 1/2 here. Just a minute, please. H bar omega c G E F naught x naught एक मिनट जरा मुझे जरा थोड़ी सी मुझे एक मिनट. So G E F naught h bar omega c over x naught is E F naught over h bar omega c. I get square here. F naught h bar omega c. I already have an x naught. I put x naught 3 by 2. So I put x naught under root this x minus L minus half. Okay. So now I have to look at this object here. H bar omega c x naught half E F naught 1/2 h bar omega c 1/2 is h bar omega c 1/2 E F naught 1/2. This means that GB x equals G E F naught bar omega c, this thing equals h bar omega c so h bar omega c, this thing equals E F naught हाँ जी sorry ये वाला इसमें x नॉट अंडर रूट है नीचे okay I just missed out that x naught under root so I need an x naught here right so that x naught this thing over here is ef naught sorry this means my gbx is g ef naught over x naught is for 3 by 2 sum over x minus L minus 1/2 where L goes from 0 to LF. So now I have this expression and I have this expression over here for the integrated density of states. Now let's plot these results. So what I'm trying to do now, here I have x and here I would like to plot two objects. I would like to plot G naught x divided by G EF naught over x naught 3 by 2. So I'm going to take everything to the left hand side because this factor is common between both of the integrated density of states. So I like to plot this and I like to plot GBx, which is normalized with respect to these variables. Okay, so I would like to make both of these plots. One, of course, has a dependence on x raised to power 1.5, and the other is this factor over here. Okay, so let's plot this. So I've already written a mathematical code for this. I defined So what I've done here, I've defined H1 to be 2 over 3 into x raised to power 3 by 2. Is there a point of it, please? So look at this. This is my H1. Now I define my other function, which is density, the integrated density of states in the presence of a magnetic field. I define first of all this term, x minus L minus half. I take the square root and I only am interested in the real values. So this is my second integrated density of states. I just find out the maximum L's that are applicable in each case. G takes up the argument L. I just map the function onto different values of L and then I just make a plot. I will upload this mathematical file as well so you can actually have a look at what's going on. Now here you will observe two curves. This axis is the x-axis, so it's the energy axis, whereas this axis is the integrated density of states axis. इसको छोड़ दो, सिर्फ pointer दे दो मुझे. अब you can find here that there is a purple curve, okay, which represents the density of states in the absence of a magnetic field. And on top of that curve, there is riding an oscillatory curve, the blue curve. The blue curve has discontinuities at certain values of x. Okay? So it has a discontinuity at L equals 1.5, discontinuity at L equals 0.5, a discontinuity at L equals 2.5, and so on. So one of them is the integrated density of states in the absence, and the other is the integrated density of states in the presence of a magnetic field. Now, how is all of this going to help us? It's going to help us because we want to find out the Fermi energy in the presence of a magnetic field. Let's move on. This is not the density of states, this is the integrated density of states. One of them is proportional to e raised to power 3 by 2. Okay. So let's move on. And we'll have this curve in our mind. So now what we are interested in finding out is how does the Fermi level change? With the application of a magnetic field. Now we know that if we take G naught at x naught, what should this be equal to? What is the integrated density of states up to the Fermi level? N. This should be equal to N, the number of electrons per unit volume. Now, if we apply a magnetic field, the Fermi level supposedly changes. So now what we have is GB. In the presence of a magnetic field, the Fermi level has changed to some new values. So suppose it's XF, right? So we would like this to be equal to N as well. This is the constraint. You apply a field, Fermi level changes, still the integrated density of states at the Fermi level, the new Fermi level must still be N, because the total number of electrons is not changing. We're not compressing the solid or expanding it, right? Concentration of electrons remains the same. But GB at XF, suppose XF is the old Fermi level, X naught, plus some change in the Fermi level. But this must equal G naught at X naught, because N must remain the same. So now if I redraw that curve over there, I have X, I have some integrated density of states. I'm putting a tilde because it's normalized. I have one curve goes like this, the absence of a field. In the presence of a field, my curve looks like this. Now suppose I just pick up some random. This is my X naught, the Fermi level in the absence of a magnetic field. Now this point must give me N. But N must remain the same, which means that if I apply a magnetic field, the Fermi level must shift to this point, because at this point the yellow curve has the same y-intercept, which means that this point is my XF and this distance is delta x. So my Fermi level must change so that the integrated density of states gives me the same value of N at the old and the new Fermi levels. That's why we plot that curve over there. So now we need to find out a solution to this equation so that we are able to tell what delta x is. So what we really need to do is the following. We have the integrated density of states and we are interested in finding the point. We are interested in solving this equation over here, right? We need to solve this equation and we would like to find out the value of delta x which solves this equation. We can solve it graphically over here. So how do we do that? So what we need to know is if we equate the two integrated density of states, what we need to know is if you look at G naught x, what must happen is that x naught 3 by 2, that's the topmost row, and the normalization factors, they're just constant with both of the integrated density of states. So I'm taking what is different. 2 over 3 x naught raised to power 3 by 2 must equal, what should it equal? It should equal LF. Now that x must be replaced by XF, the value, the new Fermi level, XF, and that XF is x naught plus delta x minus L minus half. So I need to solve this equation. Solving this equation means I need to find out delta x. Okay, I can solve this equation numerically. So there is also a constraint on LF. What is LF? LF is once again the maximum L such that L plus half is less than the new density of states, the new Fermi level, which is XF, which is x naught plus delta x. Which means that L is less than x naught plus delta x minus half. The LF is the maximum L which satisfies this constraint. And I can solve this numerically. I can use the bisection method, for example. I can pick up a certain value of delta x and use the bisection method to iteratively solve this equation. Mathematical luckily does this for me. Okay? Now I will show you how I can solve this equation and I can find delta x for different values of x naught. Remember, x naught is EF naught divided by h bar omega c. So I will find out delta x for different values of x naught. X naught is fixed, right? It's given by whatever solid we're talking about at 0 kelvins. This is the Fermi level. It's known for different, it depends upon the carrier concentration. So for different x naught, we can find out what this delta x is going to be, provided we take the sum over the appropriate L's. Okay? So we can solve this equation. So that's what I've done over here. And how can I show you that? So what I'm trying to do now is the following. Do you understand the scheme of arguments? ठीक है, argument का flow समझ आ रहा है. We have applied a magnetic field and we're going to see how does the Fermi level change, and this graphical picture is our motivation. We would like to find out the shift in the Fermi level so that n remains the same, and we have two different graphs. Alright, so what I'm trying to do here is the following. X naught, so I would like to run my code for different values of x naught. So I run it for, in the range, my x naught is 0.5 all the way up to 100. So 0.5 means my Fermi level at 0 Kelvin is 1/2 of h bar omega c. And this is 100 times h bar omega c. So this large values of k represent small magnetic fields. Small value of k represent large magnetic fields. Okay, so I create a range of x naughts. If I look at x naughts, so x naught goes from 0.5, 0.51 in steps of 0.01 all the way up to 100. Now what I do is I just initialize LF. I just initialize an array with zeros. Now what I would like to do, I would like to find out the maximum LFs possible for each x naught. Okay, so I would like to implement this constraint over here. I would like to make my L less than x naught plus delta x minus minus half, right? So what I do here is, since delta x is my solution, I don't know the solution beforehand, so I cannot calculate the LF. So as an initial guess, I choose delta x to be 1 because my upper value of L demands that I know what delta x is, but I don't know delta x. So I just choose this to be 1 initially. Delta x is between -1 and 1. I just choose it to be an extreme value 1. And then I can refine my code later, but it turns out that it does not have a large dependence upon what delta x is. Okay? So this is one assumption that I am using. So what I do is I initialize my L, and while L is less, it satisfies the constraint, I keep on incrementing L. And I take the final value to be my LF. So I get an array of LFs. So let me run this. Now I have different values of x naught, and for each x naught I have an LF. Okay, for each x naught, which I've already defined in output 145, I have an LF. So for 0.5 my LF is 0, for 0.51 my LF is 1, and so on. So I've defined my maximum values of L. Now here what I do is I just find the root of the equation, which means I'm going to solve this equation over here. This equation I'm solving. Okay? So how do I solve that equation? If you observe here, I take the real part of the square root of x naught plus delta x minus L minus half. Square root of x naught plus delta x minus L minus half. Okay? And I sum up over all the values. Now I have to do a summation, right? So I'm doing the summation here with the command accumulate. Now this accumulate does a cumulative sum. So I take the final value of this sum, which means I just implement this thing here. This thing is implemented from this location to this location. Now I need to do the proper multiplications, which means I need to multiply this thing with 3 over 2 and divide by x naught cube. So I multiply with 3 over 2, divide by x naught raised to power 3 by 2 and equate this to 1. So here what I've done, and I find the root, which means I do a numerical solution of this equation. And what is my variable? Dx. The initial choice of dx is 0. This is an initial guess. So this returns the values of dx for different values of k. Now I have an array of x naughts, and for each x naught I have the dx's. I have the shifts in my Fermi level. So this is just a numerical solution to the equation that we have over here. Okay? The quiet and flatten are just technical details, not really important. They just have ensure the proper dimensionality, etc. So I run this. It's going to take some time. There are 100 values of x naught. Alright, now there are about 9,900 values. If you look at x naught, this is my table of x naughts, okay? And if you look at roots, these are all the values of roots. Dx is 0.0055, dx is 0.048956. So I get about 9,951 solutions. For each value of x naught, I get one solution. So I just need to do some, I just play a mathematical trick so that I have these, I call these solutions dy. So now if you look dy are all the solutions. These are the shifts in the Fermi level. Now what I would like to do, I would like to make a plot between my x naught, which represents my magnetic field, and my shifts in the Fermi level. Okay, here I'm going to make, first of all, I'm going to generate that listing. So if I look at Z, in the array Z, this is my x naught, this is the corresponding shift in the Fermi level. X naught, the corresponding shift in the Fermi level. So for each x naught, for each Fermi level at the ground state, which depends upon the number of electrons per unit volume, I get a shift in the Fermi level when I apply a magnetic field. Now what I would like to do, I would just like to plot this. Here is my plot. Okay, it's a more illustrative to actually do this for fewer values of, so I just change this to 50. So I'm not going far off into the regime, I just do up to 50 points. Alright. Now look at this graph. This graph on one axis has x naught. What is x naught? X naught is EF naught divided by h bar omega c. So this is really 1 over the magnetic field, the reciprocal of the magnetic field. Right? And this thing over here is the shift in the Fermi level, the normalized shift in dimensionless units. And you see it's not symmetric, it is slightly asymmetric, it's not centered around 0, and it's oscillatory. If you look at the oscillations, probably I have the oscillations zoomed in. Okay, I don't have the oscillation, but if I were to define, if I were to zoom in into this a little bit, this spacing between two maxima is 1 unit. Okay, so delta x naught is 1 unit. This is the period of this oscillation. Whenever 1 over b, in fact, whenever x naught, which is EF naught over h bar omega c, which is, that changes by 1 unit, I get a periodic pattern, I get an oscillation. So this is the oscillation in the Fermi level as a function of the magnetic field. Remember, this is x naught. X naught is EF naught over h bar omega c. Omega c is proportional to b. So this is the reciprocal of the magnetic field, keeping everything else the same. Just a static field, right? But if you vary the field, this is going to oscillate with that field. These are time independent fields, but the field is variable. You change the field, this is the density, this is the shift in the Fermi level that you get. Okay? Now if you have an oscillatory field, then you can span different regions inside this. You can oscillate in this region. Okay. Now we would like to find out the magnetization caused by this scenario. Okay. What we have here is that the Fermi level shifts. Now we would like to find out how does the magnetization change with the magnetic field, which means we would like to find the susceptibility of such a gas in which the electrons are orbiting perpendicular to the applied magnetic field. That is, we would like to find out the effect of Landau quantization on the susceptibility. And we'll notice that that magnetization has an oscillatory dependence as well. So now what we would like to do is we would like to find out the energies. All right. Because we know, why do we want to find out the energies? We know that the magnetization is the negative of the gradient of the internal energy with respect to the magnetic field at 0 kelvins. Okay. So we want to find out the energies. So now we notice, now it's long calculation, but first of all, U naught, in the absence of a magnetic field, we know that the energies are given by this d E dash, G naught E dash. And we can into E dash, right? This is the total energy. Now, if we would like to express everything in terms of x, so what we could do, we could integrate with respect to x. And here we have 0, and here we have EF naught, which will find the total energy of the system. So we integrate from 0 to xf in our dimensionless units. So we have dx prime, we have g naught x, and we have x prime. Now this gives us a factor of h bar omega c, this gives us a factor of h bar omega c, so we get an h bar omega c squared over here. Okay? Now if we insert the value of g naught, the density of states that we did from the previous lecture, and we perform this integration, the final result is quite simple. It's simply 2 over 5, the density of states at the Fermi level at 0 field, EF naught squared. And this can also be written in the following form. This GEF naught, we know from solid state physics, is given by 3 over 2 n over EF naught, EF naught squared. So we left with 3 over 5 n times EF naught. This is the total energy in the absence of a magnetic field. Okay? It's not the average of the Fermi level, it's 3 over 5 times the average of the Fermi. This is a basic result from solid state physics. Now we apply a magnetic field. So in the presence of a magnetic field, we will just take the corresponding GB here. The GB we've already calculated in the previous lecture. That's over there. Here, this thing. Okay, so let me write this down. And then we'll solve it in the end. So UB is 1/2 G EF naught X naught under root dx prime sigma at x prime, right, 1 sigma of 1 over x prime minus L minus 1/2, and we need an h bar omega c squared with this as well, because there's a factor of e prime which is h bar omega c x prime, and this thing is h bar omega c dx prime. So that contributes to a factor of h bar omega c. Now what we would like to do is quite simple. We have half g ef naught x naught square root h bar omega c whole square. I can take the summation out, dx prime x prime over x prime minus L minus half. Okay, so this is the total energy in the presence of a magnetic field. Now for each value of L, you would like to make the square, you would like to keep the square root, whatever is inside the square root, positive. So if L is 0, you would like to start the lower limit from 1/2. If L is 1, you'd like to start the lower limit from 3/2. And here you have xf, the Fermi level in the presence of a magnetic field. So the upper limit is xf. Now if I perform this integration, you can actually use Mathematica. When I perform this integration, the final result is the following. 1/2 n over ef naught 3/2 h bar omega c 5/2 sum over all possible values of LF which are allowed, 1 plus 2L plus xf minus L minus half. Okay. This is UB. Okay. Now you just have to try this out on your own. You can't believe me. But this is actually what it comes out to be. Okay. As a proof, I can quickly show you the integration over here. So here what I've done is I've just integrated this x over the square root, x over the square root. Let's look at this. When L is 0, my lower limit is 1/2, and I get this result. 1 plus xf into this thing. When my L is 1, I get this thing. So I get xf plus some variable, xf plus some variable, which is 1 plus 2L, and inside the square root I get 4xf minus some variable, and I take commons and I get this result. So you can test this out on your own. Now what we've done is we've calculated the total energies in the presence and absence of a magnetic field. Once again, I'm going to show you it's going to be a really nice result. It's a serendipitous calculation. Very, it's serendipity. But it's going to work out, it's going to pay off at the end. Now if you observe, what I would like to do is, I would like to form the ratio UB over U naught. If I form this ratio, I get 1/2 n EF naught 3/2 h bar omega c 5/2 5 over 3 n EF naught L 1 plus 2L plus xf minus L minus half. Now there are some lucky cancellations that go on. So I'm left with 5 over 6 h bar omega c EF naught 5 raised to power 2 L 1 plus 2L plus XF minus L minus half. Now this thing luckily is 1 over x naught. So I can write this as 5 over 6 1 over x naught raised to power 5 by 2 into this term. Okay, this is my ub over u naught. Now what I would like to do, I would like to plot how does the energy change in the presence of a magnetic field. Which means I would like to find out ub minus u naught over u naught. This shows me how does the energy change in the presence of a magnetic field. Let's call this w. Could be a function of x naught. It's a function of x naught. Remember, all of the variation is embodied in the field is embodied in x naught. So this thing equals 5 over 6 x naught or 5 by 2 sum over. Now I'm going to explicitly write down xf as x naught plus delta x. Okay? Because I've already calculated the delta x's. I've calculated the shifts in the Fermi levels for a particular value of x naught. That's something I've already done, this graph that I showed you. Into x naught plus delta x minus L minus half. So this will give me the shift in the energies, the change in the energies upon the application of a magnetic field. Let's plot this change. Okay? So remember, I need to know for each omega x naught, I have a fixed value of delta x, which is the solution that I found previously. So I have a numerical range of dx's corresponding to each value of x naught, and I'm going to use those. Now, since I know delta x, I can actually calculate what LF should be. Alright? So let me show you this calculation over here. Now what I'm doing here, first of all, I'm explicitly calculating my LFs because now I know what the shift in the Fermi, I know the new Fermi levels. So here in this code, I'm calculating my upper limit to L, which I'm calling LF. So L is less than x naught plus delta x minus half. Previously I was using a value of 1 here by brute force. Now I know what my dx should be. So I'm calculating my LFs. Where should I truncate my sum up to? Now in this, here I'm calculating my new Fermi levels in the presence of a magnetic field because now I know the shifts. The shifts are denoted as dy or dx. So this is my new Fermi level in the presence of a magnetic field. Now what I'm trying to do is I'm going to construct this function over here, the change in the magnetic field, which is 5 over 6 times x naught raised to power 5 by 2, this thing over here, and then I have the summation, which I do in this piece of code. So I'm calculating W, the change in energy with the application of a magnetic field. Here I do that. Now what I do is I make a table between my x naught and my w's. My w I'm defining it as v minus 1, okay? So this is zz. Now I can plot this. This is my graph. This shows the change in energy upon the application of a magnetic field. Whenever I have free electrons which are inside a magnetic field that is applied perpendicular to the plane of the electrons. This represents the cyclotron motion, the Landau quantized levels of those electrons. So now you will observe that this is x naught. So this really is proportional to 1 over the magnetic field. This is the change in the energies. Large values of x naught, small fields shows small changes. Large field, which is this region over here, large changes. So once again I observe an oscillatory behavior. Okay? So this oscillatory behavior has a certain period. So if I would like to show that period, I can show it by zooming in onto certain number of points, let's say 3000 to 4000. I just make a smaller graph. I zoom in onto the previous graph. You see this oscillatory behavior. This is once again, I picked up a small value, range of values of x naught, and you can see this oscillatory behavior in the energy. Okay, if I would like to find out the period of this is 34, this is 35, so it's about 1 unit. Delta x naught 1 unit, which means whenever 1 over v changes such that EF naught over h bar omega c is 1, that gives me 1, it gives me periodicity. Okay, so it's an oscillatory signal. And what I could actually do, I could go further from here. If I look at this graph over here, this graph, ten more minutes please. This is W x naught. This is x naught. My graph looks like this. It's oscillatory. And if I look at this envelope, I can fit this envelope to a function. Okay? It turns out that Wx naught falls off quadratically. Okay? So I can put this equal to alpha over x naught square. Okay, let's see if that. So if I fit this function, it turns out it's an inverse quadratic function. Remember, doing things numerically is the hallmark of physics. You can never achieve a proper result without doing a numerical calculation. This can also be done analytically, as Landau originally did, but I am showing it the numerical flavor of such a calculation. So now if I make a, so how do I test this? I can test this in the following fashion. If I make a plot between Wx naught and 1 over x naught squared, and if I get a straight line and an oscillation riding on top of that straight line, then I will verify that the envelope or the mean points of this oscillation has this linear dependence on 1 over x naught square. And by the slope of this line, I can determine what alpha is. So I've done that here. So here you will observe that I make a table between 1 over x naught square on the x-axis and my w. Okay, I construct this table I call it ZZ3 and then I plot it. This is my result. It's a straight line. The period of these oscillations remains constant, but the slope of this line is alpha. Okay? The period remains constant, but the amplitude grows. This is 1 over x naught squared, so this is the varying magnetic field, B square. So the x-axis is proportional to the square of the magnetic field. As the field grows, the oscillations grow. This is another zoomed in version. Okay? Another zoomed in over a certain restricted range of 1 over x naught squared. Now I can fit this. If I fit this function, I get the value of alpha. The value of alpha is 0.1, 1 over 10. So I have determined what this value of alpha is numerically. Alright? Now, how do we go beyond this? Which means my Wx naught is equal to this thing over here. Alright? But there's also an oscillatory part. Okay? So really my Wx naught, this just looks at the mean of this oscillation. On top of this, there's an oscillatory part. That oscillatory part can be represented as 1 plus Qx naught. Correct? So my W of x naught is alpha over x naught squared 1 plus Qx naught. Lee, can you please look at the camera? So this is my Wx naught, where Q represents the oscillations. If I don't have this, I just get the mean of the oscillation. This is just the mean of the oscillation. On top of that mean, I have an oscillatory part. I need to find out what this oscillatory part is. Okay, that's fine. So my Wx naught is UB minus U naught over U naught. This is U naught alpha x naught squared 1 plus Qx naught, which means my UB is U naught plus U naught alpha x naught squared 1 plus Qx naught, which is U naught plus U naught alpha over x naught squared plus U naught alpha over x naught squared Qx naught. Now by looking at this expression over here, or this expression, I can also plot Qx naught. And I can see how does this depend upon x naught. Right? I can see how does this depend upon x naught. So what I could do, I could plot, I could take everything, I could take W, x naught, multiplied with x naught square over alpha, subtract 1 from this. This is my Qx naught. And then I can plot this. This will give me the raw oscillations, just the oscillations. Alright? Now I would like to see what do these oscillations look like. So what I have is, I make my W, I divide this W by, I divide this W by alpha, multiply with x naught square, and subtract 1 from this. That I do over here. I take my W, divide by alpha, multiply by x naught square minus 1, I generate this S. Okay, then I make a table QQ and QQ2. So I generate S, I generate Q, and if I plot Q, right, so this is a plot of my Q. Observe this plot. This is a plot of my oscillation. This is my Q. This is the raw oscillation, and you will observe that it is centered about 0. So the oscillatory part is centered about 0. Now what I would like to do, I would like to fit the envelope of this to another function. Okay? It turns out that the envelope of this is modeled by 1 over under root x naught. Okay, so let's look at that over here. My qx naught is being modeled as some beta, some constant, qx naught bar over x naught under root. Now qx naught with a bar just represents an oscillation of a fixed amplitude of say +1 -1. Okay, now this oscillation, you multiply this with some scaling factor beta, and it has a dependence on x naught. So what I could do, if I were to plot qx naught versus 1 over under root x naught, if I were to get a straight line, okay, then I can determine what this beta is going to be. So I can do that over here. I've done it. So I take 1 over square root x naught, and then I take this q that I've already determined over here, this object here that you're seeing on the graph shows how this thing, this is actually showing this thing over here. And if you look at this graph, I have 1 over under root x naught over here, and here I have on the y-axis I have SS. So what I'm doing is that I'm plotting qx naught versus this. Okay, and I get this thing over here. It's a straight line, and there's an oscillation of constant amplitude riding on that straight line, and the amplitude is growing with the magnetic field. From this I can actually calculate what the value of beta should be. So if I look here, if I go from 0.4 to say 0.8, so I make a step of 0.4 here. Here I'm going from 0.2 to 0.4. So 0.2 divided by 0.4, 0.5 is the slope. The value of beta is 0.5 here. So beta from the fit turns out to be 0.5 and the value of alpha turns out to be 0.1. Now I can insert these values in here. This Qx0 is simply some beta Q bar x0 over under root x0. So the oscillation now is represented by a function that is oscillatory of unit amplitude but depends upon under root x0 through the constant of proportionality beta. So it's a linear function of 1 over under root x0 and the slope is beta. Okay? So this Qx0 is replaced by all of this. And when this is replaced by all of this, I can actually determine what energy is going to be. So the final result is the following. My UB equals U0 plus now I take the value of U0 that I've written at the top, 3 over 5 n over n into EF0 into alpha, I'm still keeping it alpha over x0 squared plus U0 3 over 5 n EF0 to alpha over x0 squared, alpha over x0 squared into beta q bar x0 over x0 1 by half. Alright, so this is, now what I could do is I could get rid of the n's. How do I get rid of the n's? Using the formula G EF0 equals 3 over 2 n over EF0. Okay, so I can solve this for n, put this n in here and put this n in here. And another thing that I could do is the following. I have an x0. x0 equals EF0 over h bar omega c. Now omega c is EB m. Okay. Now I also know that the Bohr magneton mu b is EH bar over 2m. So this EB over m, this EH bar over m is 2 mu b. So I can write this as EF0 2 mu bb. So I can replace the x0 with this expression and I can express the n with this expression. And ultimately what I would get is the following. UB equals U0 plus 8 over 5 G at EF0 mu b square alpha b squared plus 2 raised to the power 7 by 2 5 G EF0 mu naught b raised to the power 5 by 2 alpha beta q bar x0 EF0 1/2. And you will observe that this is the energy. Now I could find the magnetization directly from minus mu b over b, partial b. I can differentiate this expression and the magnetization turns out to be minus 16 over 5 G EF0 mu b square alpha b minus 2 raised to power 7 by 2 g ef naught 1/2 mu b 5 by 2 b 3 by 2 alpha beta q bar x naught. This is my magnetization, and if I differentiate this with respect to H, once again I will get the susceptibility. Now first of all, there are two things to notice. First of all, that this magnetization is oscillatory. This represents the oscillatory term. Now these oscillations in the magnetization occur as a function of B. Observe this effect here. Higher the magnetic field, higher will be the amplitude of these oscillations. Up to this point, everything is a constant. Nothing has dependence upon. This is an oscillatory term, but nothing else is oscillatory. So all of this represents an oscillation. The oscillations grow as the magnetic field grows. And the period of the oscillation is embodied within this factor q bar. The period of that oscillation is delta x naught is 1, which is EB x naught is EF naught over H power omega c. The step is 1. So you can find out the period. The period of that oscillation is captured in here, and the amplitude of the oscillation grows as B. If you're at high temperature, when you're at high temperature, which means that kBt is much larger than H bar omega c, then this term vanishes. This term goes to a really small number, because your omega c is small, which means your magnetic field is small. So when you're at large temperatures or small magnetic fields, you cannot see these oscillations. These oscillations, by the way, are called de Haas-Van Alphen oscillations. And they are one of the most important techniques in studying the Fermi surfaces. These oscillations tell us what the Fermi surface is like. So if you look at this term over here, which survives at high temperature and low magnetic field, and if I take the derivative of this with respect to H, if I do that, then I'm left with minus alpha 16 over 5 G E F naught mu naught mu b squared. And if you look at this factor over here, this is 1.6 divided by 5, which is 0.333, 1 over 3. This is minus 1 over 3 G E F naught mu b squared. This susceptibility is first of all negative, so it represents a diamagnetic effect. This kind of diamagnetism is called Landau Diamagnetism. So this susceptibility, the Landau Diamagnetism, is minus 1 over 3 G at EF naught. Depends upon, once again it depends on density of states at the Fermi level, at 0 Kelvin. Mu naught mu b squared. And if you compare this with the Pauli paramagnetism that we derived earlier, that effect was does anyone remember that? Three over two mu naught mu b square over E F naught, right? ABTF. Now if you compare this expression with this expression, this is minus 1 over 3. This thing is 3 over 2 n over EF naught. Of course there's an n here as well. So mu naught mu b square. So this is minus 1/2 n EF naught mu b square, and this equals minus 1/3 of the Pauli susceptibility. So the diamagnetic susceptibility, first of all, it represents diamagnetism. So free electrons have a paramagnetic term as well, and they also have a diamagnetic term. And it turns out, just by luck, that the Landau diamagnetic susceptibility is 1/3 that of the Pauli susceptibility. Now I would like to show you two slides of actual results for such kinds of magneto-optic oscillations. So that you believe me that whatever I am saying is not untrue. Alright, so here what we have is a magnetic field, and instead of the magnetization we have the resistivity, and we see oscillations in the resistivity because the resistivity also depends upon the density of states at the Fermi level inside a metal, because only those electrons contribute to conduction, nothing else contributes. So you will observe that there are oscillations in the resistivity as well, and this effect is appreciable for large magnetic fields. And this effect wanes down, it de-emphasizes as you raise the temperature. So if you want to look at these magnetic oscillations, magneto-oscillatory effects in the resistivity or the magnetization, you really need to ramp up the fields. This is a large field, 50-60 kelvins, and you really need to go to very small temperatures. So these quantum effects appear only when the sample is cold or the field is so high. The oscillations in the resistivity are called the Shubnikov-de Haas oscillations. Shubnikov-de Haas oscillations. And here you will also see the change in the resistivity for different temperatures, and it's periodic in 1 over B. You will see this periodicity effect over here. And these calculations, you apply a magnetic field in different directions. You can use these results or these experiments to find out the effective mass of the charge carrier, whether it's an electron or a hole, inside that particular band structure. Here the effective mass is 0.183 times the mass of the electron. So you apply magnetic fields in different directions. The effective mass is a tensor. You will find out the component of the effective mass that is normal to the applied field. Okay, so these results are actually used in calculating the effective mass and the anisotropy of the mass tensor. So these are the Shubnikov-de Haas oscillations. The field here is applied parallel to a particular crystallographic direction. The second result is for the Haas-Van Alphen oscillations, in which the magnetic field is in this region, and here you can see those particular oscillations. And in fact these oscillations are riding on a background. This red shows the background. That background can be subtracted to actually reveal the Haas-Van Alphen oscillations. As you lower the temperature, these oscillations become more prominent, and you really need to have your sample at large enough magnetic fields. Okay. So in the Thursday's lecture, we're going to talk a little bit about the quantum Hall effect. And after that, you're going to have a midterm on Saturday, 9 a.m. I will not be here, but that's going to take place. It's going to be probably a 2-hour exam. But inshallah, see you on Thursday.